Yes, good morning, my dear children. In the previous class, we have discussed exercise 7.4 in the chapter integrals. I hope you have understood well the concepts of exercise 7.4 and we have to complete the sums which are not explained in the class. If you have any doubts in that exercise, please feel free to ask your doubts and get your doubts clarified. Today, we are going to discuss new method that is integration by partial fractions method. Integrations by partial fractions method. What is meant by partial fractions and how to integrate? A integrand is given as a partial fractions. How do you integrate? See the
Sir, are you
screen,
sharing a
all of
screen,
you.
sir?
Yes, I'm going to share the screen.
Okay, sir.
Just wait for a moment. Are you able to watch the screen? Are you able to watch the screen?
Sir, you will have to share your entire screen, sir.
Just wait for a moment. Now, is it entire screen presentation?
No, sir.
No, sir.
No. Okay, I will. No. Now,
No,
are you
sir.
able to watch the? Huh?
Nothing is shown, sir.
No, sir.
Nothing. Nothing. Okay. Now,
Yes, sir.
is the screen? Huh?
Yes,
Yes,
sir.
sir.
Are you able to watch the screen completely?
Yes, sir.
Yes. So today we are going to discuss integrals, concepts of exercise 1.5. In this exercise, we are going to discuss integration by partial fractions. Integration by partial fractions. Are you ready to listen the class? All of you be ready with a rough book and a pen. All of you be with a rough book and a pen. In the meantime, I will ask you some questions to simplify. Then to use a pen and a rough paper. Okay, right. Now come to the first point, rational function. What is meant by rational function. We have to understand what is meant by a rational function. A rational function is defined as the ratio of two polynomials in the form of p of x by q of x, comma, where p of x and q of x are polynomials in the variable x. Q of x is not equal to 0. You have already learned rational numbers. Similarly, a rational function means it is a ratio of two polynomials. In the numerator, there is a polynomial in x, and in the denominator also there will be a polynomial in x. In the numerator as in the denominator, both are polynomials in x, and the denominator is not equal to 0. This is the definition of rational function. Just like a rational number, here also we define a rational function. Now come to the second point, proper rational function. We have already studied proper fraction. Proper fraction means numerator is less and the denominator is more. Yes or no? Proper fraction means denominator is more, numerator is less. Similarly, here we define a proper rational function. Proper rational function means if the degree of p of x, hereafter p of x means considered a polynomial in the numerator and q of x is a polynomial in the denominator. Throughout this exercise, remember this point. P of x denotes a polynomial in x in the numerator and q x is also a polynomial in x in the denominator. If the degree of p of x is less than the degree of q of x, then the rational function p of x by q of x is called proper rational function. It is just like similar to proper fraction. Proper fraction in classes you studied. Proper fraction means numerator is a less number and the denominator is number. In this case, we compare degree of numerator and degree of denominator. Degree of numerator, that is p of x, is less than the degree of q of x, means degree of the denominator. Then the rational function p of x by q of x is called proper rational function. You have to understand these definitions. For example, let us take an example to understand this point. What is meant by a proper rational function? Here, 1 by x minus 1 into x minus 2 into 5x minus 7. If you observe this fraction, in the numerator 1 is there and in the denominator a polynomial in x written as a product of three linear factors. This is a proper rational function because degree of the numerator is 0. What is there in the numerator? 1. So it is also a polynomial. So its degree is 0 because the degree of a constant polynomial is 0. In 9th class itself, you have studied this point. Degree of a non-zero constant polynomial is 0. And the degree of the denominator, if you observe the denominator, it is a product of three linear factors. So to find the degree of this denominator, in the first bracket, what is exponent of x here? Tell me, what is the exponent of x here?
1, sir.
Yes. What is the exponent of x in the second factor?
1,
2,
sir.
sir.
2.
Sorry, sir. 1.
Observe and tell me the answer. What is the exponent of x in the third factor
1, sir.
1. So here degree of the first polynomial in the bracket is 1. Here also 1 and 1. So to find the degree of this denominator, we add exponent of x. Here 1 plus 1 plus 1. So 3. So we define here degree of this denominator is 3. If you compare degree of the numerator and the degree of the denominator, degree of p of x is less than the degree of q of x. That is why this proper this rational function is called a proper rational function. Understood this point? First of all, we have to decide whether the given rational function is a proper rational function or not. Let us take another example. Okay, improper fraction, improper rational function. Let us take the next point, improper rational function. In your early studies, you studied improper fraction. What is meant by improper fraction? If the numerator is equal to the denominator, or if the numerator is greater than the denominator, then the fraction is called improper fraction. Similarly here, improper rational function means if the degree of p of x throughout this exercise, remember this one, p of x denotes a polynomial in x in the numerator, and q of x denotes a polynomial in x in the denominator. If the degree of p of x is greater than or equal to the degree of q of x, then the rational function p of x by q of x is called improper rational function. This is about improper rational function. Now, let us take an example to understand this concept. Let us take the example 10x cubed plus 5x squared plus 7 whole divided by x minus 1 into x minus 2 into 5x minus 3. What is the degree of numerator? Tell me. What is the degree of the numerator? What is the degree of the numerator?
3, sir.
Yeah. What is the degree of the denominator?
3, sir.
3. So, if you observe, the degree of the numerator is 3 and the degree of the denominator is also 3. Here, the degree of p of x is equal to the degree of q of x. Therefore, the given rational function is called an improper rational function. Understood the difference between proper rational function and an improper rational function? Understood this difference between these two? Now let us take another example for improper rational function. What is the degree of numerator? Tell me. What is the degree of the numerator?
5,
4,
sir.
sir. 5.
5. Highest power of x. Highest power of x is called degree of the polynomial. What is the degree of the denominator? What is the degree of the
3,
denominator?
sir.
3. So, if you observe this rational function, it is an improper rational function because degree of the numerator is equal to 5. Degree of the numerator is equal to 5 and the degree of the denominator is equal to 3. Here, degree of p of x is greater than the degree of q of x. Therefore, the given rational function is an improper rational function. Understood the difference between proper rational function and an improper rational function?
Yes, sir.
How to identify a given rational function, whether it is a proper rational function or improper rational function? You have to find degree of numerator and degree of the denominator, and we compare the degrees of the numerator and denominator. Then we decide the given rational function is whether it is a proper rational function or improper rational function. Now come to the next point. If p of x by q of x is an improper rational function, then we divide p of x by q of x by using long division. In the number system also, if the given fraction is improper fraction, what will you do here? You will divide the numerator by denominator and we convert that into a mixed fraction. Yes or no? If the given fraction is a improper fraction, then you convert that improper fraction into a mixed fraction. Similarly, here also, if the given rational function is an improper rational function, then we divide p of x by q of x and we convert the given rational function as a mixed fraction like this: t of x plus p1 of x by q1 of x. That is, p of x by q of x is equal to t of x plus p1 of x by q1 of x, where t of x is a polynomial in x and p1 of x by q1 of x is a proper rational function. Thus, p of x by q of x is expressible as the sum of a polynomial and a proper rational function. Here the concept is, if the given rational function is an improper rational function, in that case we have to divide the numerator by denominator by long division and we convert the given improper rational function as mixed function like this: t of x is a polynomial plus one proper rational function, just like in the number system. Okay. Now come to the next point. Resolution or decomposition of proper rational function. Here in this point we are going to discuss how to resolve, how to decompose a proper rational function into partial fractions. See here, any proper rational function p of x by q of x can be expressed as the sum of rational functions, each having a simple factor of q of x. Simple factor means a linear factor. Simple factor means a linear expression, a linear polynomial. The rational functions which we shall consider here for integration purpose will be those whose denominator can be factorized. The denominator can be factorized into linear and quadratic. Linear polynomials and quadratic polynomials. In this exercise, whatever the functions, whatever the polynomials in the denominator can be expressed as a product of some linear and quadratic factors, quadratic polynomials. Each such fraction is called a partial fraction, and the process of obtaining them is called resolution or decomposition of proper rational function into partial fractions. So here a rational function will be given, proper rational function. Only proper rational functions can be decomposed. Only proper rational functions can be resolved into partial fractions. The resolution of P of x by Q of x into partial fractions depends upon mainly the nature of the factors of Q of x as discussed below. So let us see this point how to resolve partial fractions. Case 1. Case 1, when the denominator is expressible as the product of non-repeating linear factors, if the denominator is expressed as a product of non-repeating linear factors. In this case, how to write partial fractions? See this point. This is the first type questions. Let Q of x is equal to x minus a1 into x minus a2 into x minus a3 and so on, x minus an. Then we assume that here I told you previously Q of x means denominator. If the denominator is expressed as product of some linear factors, only linear factors. If you observe the first one, it is a linear polynomial. If you observe the second bracket, it is also a linear polynomial. If you observe the third bracket, it is also a linear polynomial. So these are all said to be linear factors. In this case, how to write partial fractions? Then we assume that P of x by Q of x is equal to a1 by x minus a1 plus a2 by x minus a2 plus a3 by minus a3 plus and so on plus an by x minus an. So we write the given rational function like this, where capital A1, capital A2, capital A and so on, capital AN are constants. Here we have to find A1, A2, A3 and so on. Then the given rational function can be decomposed into partial fractions. And that can be determined. These values A1, A2, A3 and so on, AN can be found by equating the numerator on RHS to the numerator on LHS. Substituting x is equal to A1, comma, A2, comma, A3 and so on, AN. Then we get values of capital letter A1, capital letter A2, capital letter A3 and so on, capital letter AN. Let us see the example how to write fractions for a given proper rational function. See this table, my children. See this table. If you observe this table, form of rational function, and the second column, form of partial fraction. See this first one, px plus q by x minus a into x minus b, comma a is not equal to b. If you observe this rational function, is it a proper rational function or not? Tell me, is it a proper rational function or not? Why it
Yes,
proper
sir.
rational function? Tell me why it is a proper rational function. How do you say it is a proper rational function?
So degree in the degree
What
of
degree, sir?
numerator is less than the degree of denominator.
What is the degree of the numerator?
1, sir.
Good. What is the degree of the denominator?
2, sir.
Yes. Here degree of the numerator is 1 and the degree of the denominator is 2. So here degree of the numerator is less than the degree of the denominator. Therefore, we confirm that this rational function is a proper rational function. Only for proper rational functions we can write partial fractions. So for this proper rational function, we write these partial fractions. Here x minus a, if you observe the denominator, x minus a is one linear factor and x minus b is another linear factor. Corresponding to every linear factor, we write one partial fraction. Say here capital letter A x minus a plus capital letter B by x minus b. These two are partial fractions. In the denominator, how many linear factors are there? Denominator in the given rational function. How many linear factors are
2,
there in
sir.
the given? So we wrote two partial fractions. Understood? Come to the second example. Px square plus qx plus r by x minus a into x minus b into x minus c. Is it a proper rational function? Is this a
Yes,
proper
sir.
rational function? Why it is a proper rational function?
So degree of numerator is less than degree of denominator.
What is the degree of the numerator?
2, sir.
Yes, very good. What is the degree of the denominator?
3, sir.
3, sir.
Yes, very good. Previously, I told you how to find degree of the denominator. Add the exponents of x in every factor. 1 plus 1 plus 1, 3. So here degree of the numerator is less than the degree of the denominator. That is why this given rational function is a rational function. So for this one, we can write partial fractions. How many partial fractions can be written? Corresponding to every non-repeated linear factor, we write one partial fraction. Here x minus a is a non-repeated linear factor, so we wrote one partial fraction a by x minus a. The second linear factor is x minus b. Corresponding to this non-repeated linear factor, we wrote another partial fraction, that is capital letter b by x minus b. And third linear factor, non-repeated linear factor, corresponding to this factor, we wrote third partial fraction, that is capital letter c by x minus c. First, we had to write these partial fractions for a given rational function. Understood?
Yes, sir.
Yes. Remark. Please observe this point, my dear children. In order to determine the values of constants in the numerators, of the type mistake THED I typed here, or I will correct it later. So in order to determine the values of the constants in the numerator of the partial fraction corresponding to the non-repeated linear factor px plus q in the denominator of a rational function, rational expression, proceed as follows. In the partial fractions, as we have discussed in the previous slide, we wrote partial fractions for a given rational function, proper rational function. There are two linear factors, we wrote two partial fractions. If there are three linear factors, we wrote three partial fractions. But in the numerator, there are unknown values. We have to find constants, the values of the constants. So to find the values in the numerator, we follow this procedure. Easily we can find the value. Replace x is equal to minus q by p. This can be obtained. This value of x can be obtained by putting px plus q is equal to 0 everywhere in the given rational function, in the given rational expression, except in the factor px plus q itself. In that factor, we should not substitute this x value. Substitute x value in the remaining part of this rational expression. Then we get the numerator constant, the corresponding numerator. Like this, we find the values of the numerators. Now, case 2. This is type 2 sums. Type 2 sums. When the denominator is expressible as the product of linear factors such that some of them are repeating. In the denominator, in the previous case, in the case 1, the denominator contains linear factors, only linear factors which are distinct, which are different from others. But here in the case 2, some linear factors will be repeated. Let us see how the linear factors are repeated. Let of x means denominator is equal to x minus a whole power k into x minus a1 into x minus a2 into x minus a3 and so on, x minus ar. If you observe the denominator, p of x means denominator only. X minus a is a linear factor, x minus a1 is also a linear factor, x minus a2 is also a linear factor, x minus a3 is also linear factor. Similarly, and so on, x minus ar also linear factor. But here, if we observe the first linear factor, whole power k is there. Whole power k means this linear factor is repeating k times. This linear factor is repeating k times. Suppose whole square is there. This linear factor is repeating 2 times. Suppose for this linear factor, whole cube is there. It means this linear factor is repeating 3 times. Understood what is meant by repeating the linear factor?
Yes.
How do you say a linear factor is repeated? Whole square, whole cube, and so on. Whole square is there, then that linear factor is said to be repeated 2 times. If the exponent of linear factor is 3, that means whole cube is there, then the linear factor is said to be repeated for 3 times. Okay, and so on. P of x by q of x is equal to a1 by x minus a plus 2 by x minus a whole square plus a3 by x minus a whole cube and so on. Ak by x minus a whole power k plus a by x minus a1 plus 2 by x minus a2 b3 by x minus a3 plus and so on br by x minus ar. If we observe these partial fractions corresponding to non-repeating factors, partial fractions like this b1 by b2 by b3 by like this. But here this leader factor is repeated k times. So we wrote here k partial fractions x minus a whole square, x minus a whole cube, x minus a whole power k. So corresponding to non-repeating factors, we assume that as it is in the case of case 1. And for each repeating factor x minus a whole power k, we assume partial fraction a1 by x minus a plus a2 by x minus a whole square plus a3 by x minus a whole cube plus and so on ak by x minus a whole power k. So since this linear factor repeated for k times, we wrote here k partial fractions like this by increasing the power to the linear factor 1 square whole cube and so on, where a1 a2 a3 and so on a and b1 b2 b3 and so on, they are also constants. Okay, this is a case, second type of problems. Also we have to find the values of a1 a2 a3 and so on, ak b1 b2 b and so on br. To determine constants, here also to determine constants, we equate numerators on both sides. Some of the constants determined by substitution, as in the case of first case. Remaining are obtained, and the remaining constants are obtained by comparing coefficients of equal powers of x and x. When we are discussing the sums, you can understand how to find the values of a1 a2 a3 a4 and so on ak and b1 b2 b3 and so on br. So this is a second step. First step is you have to finalize whether the given rational function is a proper rational function or not. Only for proper rational functions we can write partial fractions. In case if the given rational function is improper rational function, we have to transform it into a mixed one, a polynomial plus a proper rational function. And for that proper rational function, we write partial fractions. After that second step, we have to write partial fractions like this. According to the case, we write partial fractions. And the third step, we have to find these values, numerator values. Okay, this is a third step. Let us take an example. Observe this table. P of px plus q by x minus a whole square. Is it a proper rational function? Is this a proper rational function?
Yes, sir.
How it is a proper rational function? What is the degree of the numerator?
1, sir.
Very good. What is the degree of the denominator?
2, sir.
Because x minus a whole square means x minus a into x minus a. Yes or no? So 1 plus 1, 2. Here degree of the numerator is less than the degree of the denominator. That is why this is called a proper rational function. For this proper rational function, here observe the denominator. While you are writing, when you are writing partial fractions for this proper rational function, first we have to observe the denominator. In the denominator, this is a repeated linear factor. How many times this linear factor is repeated? Whole square is there. Whole square is there for this linear factor. Means this linear factor is repeated 2 times. So corresponding to this one, we write two partial fractions like this: a by x minus a plus b by x minus a whole square. Since this linear factor is repeated twice, we wrote two partial fractions. Understood these partial fractions for this rational function?
Yes, sir.
Now come to the example number 2. Px square plus qx plus r by x minus a whole square into x minus b into x minus c. Is it a proper rational function?
Yes, sir.
How do you say? What is the degree of the numerator?
2, sir.
Very good. What is the degree of the denominator?
4, sir.
Yes, 4, not 3. Degree of the denominator is 4. So here, degree of the numerator is less than the degree of the denominator. Therefore, we confirmed that the given rational function is a proper rational function. And we know that for every proper rational function, we can write partial fractions. Now, if you observe the denominator, when you are writing partial fractions, first we have to focus, we have to concentrate the denominator. Here x minus a whole square is there. It means this linear factor is repeated 2 times. That is why for this factor, we wrote two partial fractions. I'm showing by laser pointer. Are you watching this one? A by x minus a plus b by x minus a whole square. We wrote two partial fractions for this repeated linear factor. Understood these two partial fractions?
Yes, sir.
And come to the x minus b. This is a non-repeated linear factor. This is called non-repeated linear factor. So corresponding to this non-repeated linear factor, we wrote one partial fraction. Can you tell me what is the partial fraction? We wrote here, I kept that laser pointer here. What is the partial fraction I wrote here corresponding to this x b?
The c by x minus b, sir.
C by x minus b. Similarly, so the third one, x minus c, this is also a non-repeated linear factor. X minus c is a non-repeated linear factor. So corresponding to this non-repeated linear factor, I wrote another partial fraction. What is that partial fraction corresponding to this non-repeated linear factor? Tell me. I have shown by laser
The d
point.
by x
I
minus
have
c.
shown the partial fraction by laser point. Can you tell me that partial fraction at least? by observing this laser point?
The d by x minus c, sir.
By x minus c. So here we wrote 4 partial fractions. After that, this is the first step. We had to identify whether the given partial fraction is, whether the given rational function is a proper rational function or not. And the second step, we had to write fractions like this. And the third step, we had to find the values a, b, c, d. Okay, that is the third step. Case 3, third type of sums. When sum of the factors of denominator q of x quadratic but non-repeating. This is the third type of sums. When sum of the factors of denominator x are quadratic but non-repeating. Corresponding to each quadratic factor ax square plus c, we assume partial fractions by the type by ax plus b by ax square plus bx plus c, where a and b are constants. After that, we have to find the values of a and b, comparing the coefficients of similar powers of x in the numerator of both sides. So after that, we find a and b values. So if the denominator contains any quadratic factor like this, then corresponding to this quadratic factor, corresponding to this quadratic polynomial, we write a partial fraction like this: ax plus b by ax square plus bx plus c. After that, we find the values of a and b. That is the next step. Okay. Now let us see the example to understand this 3. Observe this table. My dear children, see this first form of the rational function. See 1 px plus q by x minus a whole square into x square plus b square. Is it a proper rational function? Is this rational function a proper rational function?
Yes, sir.
Tell me, what is the degree of the numerator?
1, sir.
What is the degree of the denominator?
4, sir.
Very good. Degree of the numerator is 1 and the degree of the denominator is 4. Therefore, degree of the numerator is less than the degree of the denominator. Therefore, this is this partial fraction, this proper fraction, it is a proper rational function. This rational function is a rational function. So we can write partial fractions. Observe the denominator. I told you previously, when you are going to write partial fractions for any proper rational function, observe the denominator. In the denominator, if you observe this one, x minus a whole square, this is called a repeated linear factor. How many times this linear factor is repeated?
2 times, sir.
Very good. So for this repeated linear factor, we write two partial fractions like this: capital letter A by x minus a plus capital letter B by x minus a whole square. These partial fractions are over corresponding to this repeated linear factor. Now come to the next factor. If you observe this one, this is a quadratic polynomial. Here x term is missing. X square plus b square means some constant. X term is not given. This is a quadratic polynomial. Here we cannot find factors for this. We cannot find factors for this. In this case, this quadratic polynomial is called irreducible quadratic polynomial. If a quadratic polynomial cannot be expressed as a product of two linear polynomials, then the quadratic polynomial is called irreducible quadratic polynomial. So here this is a irreducible quadratic polynomial. So corresponding to this irreducible quadratic polynomial, we wrote a partial fraction cx plus d by x square plus a square. Understood this partial fraction corresponding to this quadratic polynomial?
Yes, sir.
In the numerator, we write x term plus a constant. Okay. In the case of quadratic polynomial, when you are writing partial fraction, in the numerator, we write x term plus a constant. Okay. Now, observe the next example. Px square plus qx plus r whole divided by x square plus a square into x minus b into x minus c. Is this rational function a proper rational function?
Yes, sir.
What is the degree of the numerator?
2, sir.
Yes. The degree of the denominator?
4, sir.
Very good. So here, degree of the numerator is less than the degree of the denominator. That is why this rational function is said to be a proper rational function. So you know that for every proper rational function, we can write partial fractions. When you are going to write partial fractions, I told that point clearly. We have to concentrate the denominator. We have to focus on the denominator while you are writing partial fractions. What is this first factor? Tell me. It is a irreducible quadratic polynomial. If you observe the factor in the denominator, x square plus a square, this is called irreducible quadratic polynomial. Means this quadratic polynomial cannot be written as product of two linear factors. That is why this quadratic polynomial is called irreducible quadratic polynomial. So corresponding to this irreducible quadratic polynomial, we wrote a partial fraction. See second box, ax plus b by x square plus a square. So corresponding to this irreducible quadratic polynomial, we wrote one partial fraction. Now come to the next factor. Which type of factor this one? Which type of factor this one? Non-repeated linear factor. Yes or no? If you observe this factor, x minus b, if you observe the second factor, x minus b, this is a non-repeated linear factor. So corresponding to this non-repeated linear factor, we wrote a partial fraction. What is the partial fraction I wrote for this non-repeated linear factor? Can you tell me? Can you tell me?
C by x plus x minus b, sir.
Yes. C by x minus b. Now come to the last linear factor. Last linear factor. What is the last linear factor in the denominator? Tell me. What is the
X
last
minus c,
linear
sir.
factor? X minus c. Which type of linear factor? It is also a non-repeated linear factor. This linear factor is also a non-repeated linear factor. So corresponding to this non-repeated linear factor, I wrote a partial fraction. What is that partial fraction I wrote here? Tell me.
So d by x minus c, sir.
D by x minus c. So like this, we had to write partial fractions for a given proper rational function. This is a step 3. Okay. After that, we find the values a, b, c, and d. We discuss this point later when we are solving the sums. We discuss how to find the values of a, b, c, and d. Okay. Now, case 4. This is case 4. Total maximum 5 cases are there. Total 5 cases. This entire exercise is divided into 5 types of sums. Case 1 means type 1. Case 2 means type 2 sums. Case 3 means type 3 sums. Case 4 means type 4. This is very rare, type 4. Case 4 is a very rare case. This type of questions were not given in the textbook. This type of questions will not be given. Case 4 type questions are not given in the textbook. Just for your knowledge, I am explaining this case 4. Okay. Now come to this case 4. When q of x contains repeated and non-repeated irreducible quadratic factors. Previously, I told you irreducible quadratic factor means a quadratic factor. That means the quadratic polynomial cannot be expressed as a product of two linear factors. That is the meaning of irreducible quadratic polynomial or irreducible quadratic factor. Then corresponding to every repeated quadratic factor ax square plus bx plus c whole power p. This irreducible quadratic polynomial is repeated for p times because whole power p is there. So with the help of the exponent of this quadratic polynomial, we can say that how many times this quadratic polynomial is repeated. The whole power p is there. Therefore, we can say that this quadratic polynomial is repeated for times. There exist p partial fractions of the form. So, since this irreducible quadratic polynomial is repeated for p times, we write p partial fractions. How to write partial fractions? P partial fractions. Observe this step. a1x plus b1 by ax square plus bx plus c plus a2x plus b2 by ax square plus bx plus c whole square plus a3x plus b3 by ax square plus bx plus c whole cube plus and so on. Apx plus p by ax square plus bx plus c whole power p. How many partial fractions we here? Tell me. How many partial fractions we wrote? How many partial fractions we here? Tell me.
P times, sir.
Corresponding to this p times repeated irreducible quadratic polynomial, we wrote p partial fractions. Here in the numerator a1, a2, b2, a3, b3, b, and so on, ap, bp, these are all constants. We find these values later. Next step, that is the next stage. Okay. So first of all, you have to know how to write partial fraction. After that, we find the numerator values. Let's see an example for this case 4. Observe this table. Px plus q by x square plus a square whole square into x square plus b square. Is this rational function a proper rational function? Is this rational
Yes, sir.
function a proper? How do you say? What is the degree of the numerator?
1, sir.
Very good. What is the degree of the denominator?
3, sir.
Not 3. Not 3. See here x square. X
6,
square.
sir.
6. Here x square whole square means we get here x power 4. If we expand this one, we get here x power 4. Highest power of x in this brackets, we get x power 4. Whereas here x square, highest power of x. 4 plus 2 is 6. Understood? Degree of this denominator.
Yes, sir.
So here degree of the numerator is 1. Degree of the denominator is 6. Degree of the numerator is less than the degree of the denominator. Therefore, this rational function is a proper rational function. And we know that every proper rational function can be written as a sum of partial fractions. For every proper rational function, we can write partial fractions. I told you, when you are writing partial fractions for the given proper rational function, we have to concentrate denominator. We have to focus on the denominator. If you observe the denominator, if you observe this first factor, this is a quadratic polynomial, quadratic factor, but it is repeated for 2 times. S on a whole square is there. This is a quadratic polynomial or quadratic factor. Whole square is there, means this quadratic polynomial is repeated for 2 times. So corresponding to this repeated quadratic polynomial, we two partial fractions like this: ax plus b by x square plus a square plus c d by x square plus a square whole square. Understood these two partial fractions? Understood these two partial fractions corresponding
Yes,
to
sir.
this repeated quadratic polynomial. And what is the next factor? This is also a quadratic polynomial. It is non-repeated. Whole square, whole cube, like this, not given. Means this is a non-repeated quadratic factor. So corresponding to non-repeated quadratic factor, what is the partial fraction I wrote here? Tell me. Corresponding to this non-repeated quadratic factor. What is the partial fraction?
So ex plus f by x square plus b square.
Yes, plus ex plus f by x square plus b square. Like this, we had to write partial fractions for the given proper rational function. After that, we find the values of a, b, c, d, e, and f. And after that, we go to integration. First of all, we had to write the given proper rational functions as sum of partial fractions. We have to decompose. We have to resolve the given proper rational function into partial fractions like this. Different cases we have discussed here, different cases. Each case is said to be type 1, type 2, type 3, type 4, and so on. Okay. Now, important point. Observe this important note. If a rational function contains only even powers of x, if it contains even powers of x in both the numerator and denominator, then to resolve it into partial fractions, we proceed as follows. In case this is a case, if the given rational function contains only even powers of x in both numerator and denominator, then to resolve it into partitions, we proceed as follows. Step 1. Put x square is equal to y in the given rational function. That is the first step. Next, step 2. Resolve the rational function into partial fractions. Solve the rational function obtained in step 1 into partial fractions. That is step 2. Next, step 3. After resolving the rational function into partial fractions, we replace y by x. We replace y by x. For this important point, see the example 14, page number 320. See the example 14, the page number 320, and question number 18. Question number 18 in the page number 323, the textbook. These two questions are based on important note. These two questions are based on this important note. Okay, my children. Right. This is the concept of exercise 7.5. These are the concepts of exercise 1.5. Now, I'm going to present a video. All of you look at the video. Just wait for a moment. children, welcome to the mathematics class. Today we are going to discuss in this chapter. We are going. So, my dear children, welcome to the mathematics class. Today we are going to discuss integral. In this chapter, we are going to discuss the sums in the exercise 7.5. Page number 322. The previous class, now I am going to show a video. All of you watch this video carefully, my dear children. Today we are going to discuss integrals. In this, the degree of this denominator can be found by adding the exponents of x. What is the exponent of x here? 1. Here exponent of x is 1. So 1 plus 1, that is 2. Understood this step, my children, how to find degree of a polynomial which is given in this form. Okay, my children, right. Then the degree of p of x is here. Degree of p of x is less than degree of first we have to confirm this statement whether the degree of p of x is less than the degree of q of x or not. Yes, 1 is less than 2, isn't it or not, my children? Right. Therefore, the given rational function is a proper rational function. Isn't it or not, my dear children? It is a proper rational function. Therefore, integrand is a proper rational function. The degree of p of x is less than the degree of p of x. Then it is a proper rational function. First of all, we have to confirm this one. Otherwise, we have to divide the numerator by denominator. We have to convert. We have to transform this improper rational function proper rational function by using long division. Okay, my children, understood this point? Right. So we confirmed here the given integrand is a proper rational function. Only for proper rational function we use the integration by partial fractions method. Okay, my children, right. Now let us take the integrand. What is integrand here? X by. So let x by 1 into x plus 2. This is a type 1 problem. In this one problem, the denominator contains only non-repeated linear factors. X plus 1 is a linear factor, X plus 2 is another linear factor, both distinct linear factors, isn't it or not, my children? So non-repeated linear factors. Denominator contains non-repeated linear factors. For every corresponding to non-repeated linear factor, we write a partial fraction like this: a by x plus 1. Let us take this first non-repeated linear factor. Corresponding to this non-repeated linear factor, we write a partial fraction: a by capital letter A plus 1. Understood this term, my children? Right. Plus another non-repeated linear factor, that is x plus 2. Corresponding to this non-repeated linear factor, we write a partial fraction, another partial fraction. Understood this second partial fraction, my children? These are partial fractions. We are composing, we are splitting this entire rational function into two partial fractions like this. Okay, my children, understood this step? Right. Let us assume that this is equation 1. Okay, my children, listen the steps carefully, my children. Integration by partial fractions method. Okay, my children? Right. Now we have to, now the is to find the values of A and B. Okay, my children? Right. This implies we write LHS as it is x plus 1 into x plus 2. Now come to RHS. Let us simplify RHS. Take LCM for the denominators. We take the LCM for the denominators. X plus 1 into x plus 2 is the LCM for these two denominators. Understood this LCM, my children? Right. Now let us write the numerator. A into x plus 1, just like a cross multiplication. A into x plus 2 plus b into x plus 1. Understood this numerator, my children? Here this factor gets cancelled. What will be left here? X plus 2. So x plus 2 into numerator. Plus here x plus 2 gets cancelled. Which factor will be left here? X plus 1. So b into x plus 1. Understood this step, my children? Right. Now on the both sides, denominator gets cancelled. X plus 1 into x plus 2. Okay, my children, understood this step? Right. This implies x is equal to, what is left here? X is equal to a into x plus 2 plus b into x plus 1. A into x plus 2 plus b into x plus 1 is left in RHS. Okay, my children, understood this step? Right. Let us assume that this is equation 2. This is equation 2. In this equation 2, we have to substitute x is equal to minus 2. What is the linear factor here? X plus 2. In rough work, take the linear factor. What is the first linear factor here? X plus 1. Okay, my dear children. Take x plus 1 is equal to 0. We have to do this rough work in the rough paper. Okay, my dear children. To substitute the value of x, we have to find x is equal to minus 1. So take the first linear factor in rough work and write is equal to 0. We have to write this equation. Okay, my children. From this equation, you have to find the value of x. What is the value of x? You got here x is equal to minus 1. So substitute x is equal to minus 1 in the equation 2. Okay, my children. Put x is equal to minus 1 in the equation. Then we get in LHS as well as in RHS, we substitute x is equal to minus 1. Okay, my children, in LHS x is there, so I wrote minus 1 is equal to a into minus 1 plus 2. X is there, so we are substituting x is equal to minus 1 plus 2 plus b into minus 1 plus 1. Understood this step, my children? In this equation 2, we substituted x is equal to minus 1. Then we got this step. Children, understood this step? Right. This implies minus 1 is equal to, let us simplify 2 minus 1. What will you get? 1 into A only. I'm calculating this entire part in our mind and I wrote directly this term. The first term is A only. Plus, what will you get here? Minus 1 plus 1. What will you get? 0. 0 into B. 0. Isn't it or not, my children? So plus 0. I am not writing that's the second term plus 0. Understood this point, my children? Right. Minus 1 is equal to A. This implies A is equal to minus 1. A is equal to, this is the value of A. So we got the value of A. Now we have to find the value of B. These steps, my children. To get the value of B, take the second linear factor in rough work. We follow this figure. Okay, my children. Understood? Right. So we got here the value of A. Similarly, we have to find the value of B. Then what is the second linear factor? X plus 2. Isn't it or not, my children? In rough work, write the second linear factor, that is x plus 2. Okay, my children, is equal to 0. We have to write this equation to find the value of x. As we have followed to find the value of A, we follow the same steps here. Okay, my children, this implies x is equal to minus 2. X is equal to minus 2. We have to substitute x is equal to minus 2 in the equation 2. Okay, my children, understood this step? Right. X is equal to minus 2 in equation 2. In equation 2, we get, in this equation 2, let us substitute x is equal to minus 2 in this. This implies here LHS x is there, so minus 2 is equal to, first term A into x plus 2. So A into minus 2 plus 2, A into minus 2 plus 2 plus B into minus 2 plus 1. So this is step, and children, in this equation 2, we substituted x is equal to minus 2. Then we got to this step. So this is step, my children. Right. Now let us simplify. Okay, my children. That implies minus 2 is 2. Here A into minus 2 plus 2. What we get here? 0. A into 0. 0. So I am not writing that term. I am not writing first term 0. Now come to the second term. B into minus 2 plus 1. What will get here? Minus 1. So finally, after simplification, what will get? Minus 1 into B. Minus B. Understood this step, my children? Right. This implies minus minus gets cancelled. B is equal to 2. Found the value of B also. We found here the value of A, that is minus 1. Here we found the value of B, that is B is equal to 2. Now we substitute these two values. By substituting these two values, A is equal to minus 1, is equal to 2 in the equation 1. We substitute these two values in the equation 1. What is the equation? Understood these steps, my dear? To find the values of A and B.
Yes, sir.
After writing partial fractions, how to get the values of A and B. Understood these steps? Equation 1, substitute A is equal to minus 1 and B is equal to 2 in the equation 1. In the equation 1, we get x by x plus 1 into x plus 2, x by x plus 1 into x plus 2 is equal to a by, we wrote a by x plus 1. What is it here? Minus 1 by x plus 1 plus b by x plus 2 in the equation 1. Okay, children. What is b here? 2. 2 by x plus 2. Okay, my children. By substituting these two values in the equation 1, then we get this step. Okay, my children. Now we integrate on both sides. Integrating on both sides. Integrating on both sides. Then what will you get? Integral x by x plus 1 into x plus 2 dx is equal to integral minus 1 by x plus 1 plus 2 by x plus 2 dx. Okay, my children, we are doing the integration on both sides. Then we get to this step. For this equation, we are integrating on both sides. Okay, my children, understood? Right. This implies in assume this entire integral as capital letter I. Okay, my children. This implies capital letter I is equal to, come to the RHS part. Integral of two terms are there. So we can find the integral of these two terms separately. Okay, my children. Writing directly minus integral of 1 by x plus 1 dx plus 2 into, because 2 is a numerical coefficient, I am writing it before integral sign, 1 by x plus 2 dx. Understood this step, my children? Here I am finding the integral of these two terms separately. So I wrote this step. Understood this step, my children? Right. This implies this is equal to minus, it is in the form of integral 1 by ax plus b, a linear expression. A linear expression. Then what is the formula? Log mod ax plus b. Log mod into 1 by x means log mod x. Here linear factor is there, so log mod x plus 1 by, what is the coefficient of x here? 1. Understood? Understood this is the first term, right? Plus 2 into it. This is also in the form of integral 1 by ax plus b, a linear factor, linear expression, log mod x plus 2 by coefficient of x is 1. Understood this step, my children? Right. Writing here formula because integral 1 by ax plus b is equal to 1 by a integral 1 by ax plus b. If the linear factor is, the linear expression is there in the denominator, then its formula is 1 by a log mod ax plus b. Okay, my children, by using this integral formula, I wrote these two terms. Understood this step, my children? Right. This is equal to minus log mod, integration part is over. We are simplifying the answer. Now it is in the form of m log a. This can be written as log mod x plus 2 whole square. Isn't it, my dear children? Because m log a is equal to log a power of m, where m is equal to 2, a is equal to x plus 1. By using this logarithmic property, we wrote the second term as log of x plus 2 whole square. Understood this step, my children? Right. Again, here, this is log a minus log b. What is the formula? What is the logarithmic property? Log a minus log b. Log of a. So log of x plus 2 whole square by mod x plus 1. Because log a minus log b equal to log of a by b. Log a minus log b is equal to log of a by b by using this logarithmic property, where a means a plus x plus 2 whole square, b means minus 1. Understood this step, my children? Right. So simplification part is also over. This is the last step. This last step, what should we do? We have to add constant of integration. Okay, my children. So log mod x plus 2 whole square by x plus 1 mod x plus 1 plus c. Understood this last step, my children? Right. Log of okay, my children? Understood? Right. Come to the question number 3. My children, now the time is 10 past 31. Now you can leave the meeting and write the class. Okay.
Okay, sir.
First 5 sums. The 5 sums are of the same type in the exercise. 5. First 5 sums are of the same type. Please try the first 5 sums in the exercise 7.5 by yourself. Okay.
Okay, sir.
Okay. Wish you happy in year in advance.
Same to you, sir.
Okay. Thank you.
Thank you, sir.
Okay. Now you can leave.